This episode is brought to you by my friends at Patreon, and, once again, by Singularity G3, whose images have given life to this journey since it began. Hello, fellow Seekers. This is the long-promised collab that scheduling conflicts forced me to postpone. Please let me introduce you to my fellow space YouTuber, Trolligi. Check out his channel, without whom I could not have begun this series.
Hey everyone, Trolligi here. Not unlike Nick, I'm a slightly smaller astronomy YouTuber who likes to shed light on various astronomical discoveries, especially ones which are more obscure and haven't been talked about on YouTube very much, or at all. Most of my space videos are on topics relating to stellar evolution, nearby galaxies, black holes, and exoplanets. You may enjoy my videos if these topics interest you, as I'm sure they do given that you're here. But don't click away yet, watch this video first.
Thanks, Trolligi. While our local and wider interstellar neighborhoods have been recently mapped thanks to the efforts of Kevin Jardine, no such comprehensive map, at least as far as I can find, exists for our local group of galaxies. So Trolligi approached me with a staggeringly comprehensive database of every nearby galaxy in order of distance, backed up by very recent citations. Well, I wasn't about to say no to that. So this journey will be somewhat different from the previous. For one thing, Trolligi will be joining me at the helm. For another, rather than jumping across the map, we will simply be visiting the galaxies in order of distance from ourselves, regardless of where in space they happen to actually be. This will be a long trip, but all good journeys need preparation. And for that, first, we must step back 1,000 years. The stars shone like studs of iron in a black shield sky. The gray, mile-high desert of the Persian plateau was merciless. Cold winds blew from the frigid steppe, presaging the caravans of camels bringing their cargoes of silk from the distant east. The bazaars of the great city of Isfahan were silent, traders long since gone to their beds. But atop a high platform, Adud al-Dawla, Caliph of the Buyid Empire, was arguing about the stars. He had asked two astronomers, one named Abd al-Rahman Al-Sufi, the other an anonymous hack, to identify a specific star that had risen on the eastern horizon. The hack fumbled and vacillated, but Al-Sufi noted derisively that his rival had clearly done little observing of his own, and had instead relied entirely on Ptolemy's star charts, forgetting that they must be adjusted by 12 degrees to account for 800 years of equinoctial precession. The slow drift of the zodiac, caused by an almost, but not quite, imperceptible wobble in Earth's rotation. Al-Dawla immediately hired Al-Sufi as his personal tutor, and sent him to head up a new observatory in the southern city of Shiraz, though, like every royal astronomer who has or will ever live, Al-Sufi had to buy his own instruments. I have no idea if this story is true. I found it on an iffy webpage and haven't been able to verify its sources. But I think it illustrates very well the driving force of Al-Sufi's mathematical and astronomical life, putting Ptolemy in his place. Unlike many earlier or indeed later scholars, the astronomers of the Islamic Golden Age, a vaguely defined period lasting roughly from 800 to 1300 AD, were not content to simply rely on Claudius Ptolemy, the great Greek astronomer and mathematician whose works, particularly the Almagest and the Catalogue of Stars, were the canon for astronomy from the fall of the Roman Empire until the invention of the telescope, but checked and corrected his errors through their own observation. Al-Sufi himself believed, as many after him have, that Ptolemy did not perform any of his own observations, but simply relied on the catalogues of earlier astronomers, such as Hipparchus and Menelaus. Though, because his estimates for the speed of precession were off, 1 degree every 100 years, rather than every 72, his charts were slightly in error. Published in 964, Al-Sufi's Book of the Shapes of Stars, usually translated as the Book of Fixed Stars, is the most important astronomical text of the medieval period. Its catalogue employed 3 grades of stellar brightness, rather than Ptolemy's 2. It included more than 40 stars not mentioned by Ptolemy. It corrected Ptolemy's errors, and is, along with an Arabic translation of the Almagest, the main reason the majority of star names in the West are Arabic. But to modern astronomers, his legacy lies in a tiny scribble he added above one of the stars in Andromeda's belt, now called New Andromedae, in which he noted a, quote, little cloud, or nebulous smear. This little cloud was apparently well known to the sky watchers of Isfahan at the time, but Al-Sufi was, as far as we know, the first to record it. Why him, and why then, when the cloud is visible, albeit with effort, to the naked eye, is unknown. Some have suggested that the Mul-Apin, the Babylonian star chart, composed in 1000 BC, that forms the basis for Western astronomy, may have recorded it as well, but this is uncertain. Although it would not be known for nearly 1,000 years, Al-Sufi's little cloud was the most distant object ever observed by human eyes. So far, in fact, that even modern minds struggle to comprehend it. How much more so for a world in which the realm beyond Saturn was considered the domain of God. For centuries, Al-Sufi's little cloud was called the Andromeda Nebula. Today, we call it the Andromeda Galaxy. The distance to the Andromeda Galaxy cannot be grasped in any meaningful sense, but I will try to convey it to you. The distance from Earth to Pluto is about 5 billion kilometers. The distance from Earth to Andromeda is about 5 billion times that. I said before that science has a strange amnesia about its own history, that our solar system is just one of billions in a vast galaxy, and that galaxy, just one of billions in a universe of galaxies, is taught to children today as if it were carved in stone by ancient prophets keen to engender an existential crisis in their flock. But it has been known for barely 100 years. In 1924, Edwin Hubble of the Mount Wilson Observatory in California identified a Cepheid variable in what was then still called the Andromeda Nebula. Cepheid variables are what is known in astronomy as standard candles. They pulse regularly, and the lengths of these pulses are in direct proportion to their intrinsic brightness. Thus, by timing their pulsations, it is possible to determine exactly how bright they are, and thus how far away they are. In fact, Hubble had underestimated the distance. He had believed the Andromeda Galaxy to be 1 million light-years away. It is actually 2.5 times farther than that. That galaxies are clustered into groups had been known for a century, but Hubble was the first to precisely measure their distances, and in 1936 noted that a particular cluster of galaxies was much closer to our own galaxy than to others. Somewhat unimaginatively, he christened this assemblage the local group. Given that his observation of redshift led to the discovery that the universe was expanding, Hubble makes a good case for being the greatest observational astronomer since William Herschel, and possibly since Galileo. Our local group of galaxies is slightly misnamed. It is not one group, but 2. One centered on our home galaxy, the Milky Way, the other centered on Andromeda, separated by about 25 Milky Way diameters. The total diameter of the local group, including its outlying galaxies, is about 3 megaparsecs. For those just joining this journey, a parsec is about 3/4 the distance to our nearest star. A kiloparsec is 1,000 parsecs, and a megaparsec is 1,000,000 parsecs. Andromeda is the larger of the 2, being about twice as wide and 30% more massive than the Milky Way, and is likely to have more satellite galaxies, though its distance makes an accurate tally difficult. These two groups are moving toward each other at 123 kilometers a second, and in about 5 billion years will collide to form a single group, centered on a single, bloated, aging elliptical galaxy that, for lack of a better name, astronomers dub Milkomeda. A half-trillion years or so after that, all the satellite galaxies of the local group will fall into their slowly dying mother, and the local group will become one gigantic galaxy. If we somehow manage to reach this distant time, it will take some doing, as both Earth and the Sun will be long dead by then. Let's hope we have good records. At that point, the universe's expansion will have sent all other galaxies beyond the cosmic light horizon, removing them forever from our sight, and leaving our galactic home a guttering ember in a black void as wide as the known universe. As with all things extragalactic, no one is entirely sure how many galaxies are in our local group, because our own galaxy is permanently in the way. Of the 140 or so we do know, the vast majority are tiny dwarf galaxies. About 90% the mass of the local group is contained in the Milky Way and Andromeda. The reason we call it the local group, rather than the Milky Way, Andromeda, and hangers-on, is the Triangulum galaxy, a smallish spiral galaxy that is probably a satellite of Andromeda. But even Triangulum is just a 20th the Milky Way's mass. Before examining the local group in detail, I feel it is important to give a sense of its location. The local group sits within a space called the local volume. Prepare yourself. Astronomers fixate on the word local more than the League of Gentlemen. A sphere roughly 22 megaparsecs across, comprising roughly 500 galaxies. Those closest to the Milky Way are contained in 7 clusters, each, other than the local group, named for their dominant galaxy. The IC 342 group, the Maffei 1 group, the M81 group, the M94 group, the Sculptor group, and the Centaurus A group. IC 342 is a demure-looking spiral about 3/4 the size of the Milky Way. Its location near the plane of our galaxy makes it difficult to observe, granting it the name the Hidden Galaxy. It has relatively few satellite galaxies, and was once considered a component of the larger Maffei group, but is now believed to be closer to us, at just 3 megaparsecs. Maffei 1, named for the pioneering infrared astronomer Paolo Maffei, who discovered it, and Maffei 2, hiding behind the Heart Nebula in 1967, is a preview, albeit slightly smaller, at just 3/4 our galaxy's diameter, of how our galaxy will appear in about 5 to 10 billion years' time. A distended, box-like elliptical galaxy formed from the past collision of 2 giant spirals, red with the light of dying stars. M81, or Bode's galaxy, is a beautiful spiral galaxy of the so-called grand design type, meaning that, unlike our own galaxy, it has prominent and well-defined spiral arms. Discovered in 1774 by Johann Bode, the man who named Uranus, it is about the same size as the Milky Way, though it contains a supermassive black hole nearly 20 times larger than ours. Gravitational interactions between it and its brother, M82, have pulled its hydrogen into filaments, whilst at the same time sending gas back towards its center, leading to massive star formation there. M94, or the Cat's Eye galaxy, is a spectacular double-ringed spiral about half the size of the Milky Way, located about 5.2 megaparsecs from Earth. The rings form at resonance orbits, and their inner ring is the site of star formation, driven by the bar churning at its core. The Sculptor galaxy, also known as the Silver Coin galaxy, is a spiral galaxy about 20% larger than the Milky Way, currently undergoing a surge of star formation. This star formation is so intense that it generates a rushing wall of stellar winds, which, ironically, blast hydrogen from the core into the halo and ultimately act to choke star formation. Centaurus A is the closest active galaxy to Earth, at about 4 megaparsecs. Its gigantic supermassive black hole, 13 times the mass of ours, accretes matter at such a rate that it blasts a jet from its poles at relativistic speed, 1 million light-years into space. Despite being just 50% the diameter of the Milky Way, it is a similar mass. It is currently undergoing a burst of intense star formation, likely the result of a recent merger. These galaxies are among the group known as the Council of Giants, the 12 largest of about 60 galaxies that share a common velocity with the local group, forming a co-moving structure 7 megaparsecs wide but only half a megaparsec thick, known as the local sheet. The local sheet forms one wall of the local void, a vast bubble of virtually nothing 60 megaparsecs across, and growing. The local sheet is retreating from the void at 260 kilometers per second, drawn by the power of the distant Virgo cluster. 17 megaparsecs from Earth, 4 megaparsecs wide, and comprising a quadrillion solar masses of material, the Virgo cluster is the dominant structure in our local region of the universe, and shepherds the 33 megaparsec wide Virgo supercluster, also less inspiringly called the local supercluster, of which our local group is just a minuscule fraction. The Virgo supercluster is in turn a component of the 159 megaparsec wide Laniakea supercluster, a flow of about 100,000 gravitationally directed galaxies, all drawn toward a mysterious entity known as the Great Attractor, a 10 quadrillion solar mass object currently hidden by the band of the Milky Way, to which much of our local universe is moving at 700 kilometers per second. And on that twinge of cosmic horror, let us return to our local group. As I said, our local group comprises 2 large galaxies, the Milky Way and Andromeda, and their satellites, all on a slow collision course. Our trip begins with those closest to our home galaxy. Keep in mind that this list is constantly evolving and that new galaxies are being discovered all the time, as the boundary between galaxy and star cluster becomes ever more blurry. In fact, to explain their existence as galaxies, astronomers have concluded that they are dominated by dark matter. Also, all the galaxies we'll be discussing here are of the exact same type, dwarf spheroidals, small, low-luminosity galaxies with mostly ancient stars. The first galaxy on our trip is, well, not a galaxy. At least, not anymore. The Canis Major Overdensity is a sideways, sausage-shaped clump of about 1 billion mostly old red giant stars located about 7.5 kiloparsecs from the Sun, within the disk of the Milky Way, closer to us, in fact, than the galactic center. It forms the core of the Monoceros ring, a stream of stars that encompasses the entire band of the Milky Way. Many argue that this clump is a dwarf galaxy that ours have only recently consumed and not quite digested. But others argue that because both it and the ring lie near the warp in the Milky Way's disk, they are simply an observational artifact of said warping.
Our second, and this time actually a real stop, is Ursa Major III, a mere 10 kiloparsecs from the Sun. Despite being so close to us, suggesting that it might have been discovered a long time ago, it was only discovered in late 2023 on account of its truly extreme faintness. Ursa Major III is by far the dimmest galaxy that has ever been discovered, and the entire stellar system is only about as bright as Altair. This, coupled with Ursa Major III's tiny size being just 6 parsecs across, which is over 4,000 times smaller than our galaxy, suggests that Ursa Major III also has the lowest stellar mass of any known galaxy, at just 16 solar masses, as well as the lowest star count of any known galaxy, at between 40 to 80 stars, most likely around 57. 11 of these stars have been identified by the Gaia satellite. It is natural to doubt the galactic nature of this object, as it is smaller than many star clusters and nebulae. However, the incredibly high mass-to-luminosity ratio of 6,500 solar masses per solar luminosity indicates the existence of a massive dark matter halo, confirming that this is indeed a true, albeit hilariously small, dwarf galaxy. The extreme age of its very metal-poor stars, which have an average metallicity just 0.6% that of the Sun, suggests it is at least 11 billion years old, almost as old as the Milky Way itself. This also suggests a very high dark matter density within the galaxy, meaning that it is a great place to observe possible gamma rays resulting from the annihilation of dark matter particles.
At a distance of 21.5 kiloparsecs, we find another questionable recent galaxy, Draco II. Discovered in 2015, Draco II is extremely metal poor, between 100th and 1,000th that of the Sun, meaning that it is very old. Indeed, its stars are estimated to be roughly 13.5 billion years old, just 300 million years younger than the universe itself. Like Ursa Major III, it is very faint, just 180 times as luminous as the Sun, and very small, just 38 parsecs across. Despite this, Draco II is too widely dispersed to be a globular cluster, and fits a metallicity to luminosity relation typical of dwarf galaxies. It orbits the Milky Way in an elliptical, near-perpendicular path, reaching its highest point 153 kiloparsecs from the galactic center. This is close enough for Draco II to be disrupted by the Milky Way's tidal force.
Slightly further out, there lies another tiny dwarf galaxy, Segue I, located in Leo at a distance of about 23 kiloparsecs. First discovered in 2006, Segue I is, again, barely a galaxy. It's just 48 parsecs across, and isn't much brighter than Draco II, with a combined luminosity of just 280 times that of the Sun. It has a total stellar mass of only about 1,500 solar masses, and assuming a mean stellar mass of 0.3 suns, has only about 5,000 stars in total. Segue I is what is known as a first galaxy. It underwent just one period of star formation, lasting just 30 to 50 million years, just 500 million years after the Big Bang, after which its stellar population has remained relatively unchanged. This is in contrast to many other ultra-faint dwarfs, which formed stars for an extended period after their first post-formation starburst phase. Segue I is noticeably elongated. It is about twice as long as it is tall. This indicates that the galaxy is slowly being pulled apart by the Milky Way's tidal forces as it orbits our galaxy. Its name, incidentally, comes from the Segue program, the slowed extension for galactic understanding and exploration.
At about the same distance from the Sun, we find Tucana III, a similar ultra-faint dwarf galaxy. It is 68 parsecs across and shines with a measly total brightness of 280 suns. Tucana III has been tidally disrupted by the Milky Way, as seen from tidal tails which extend for thousands of light years from both sides of the galaxy. Tucana III has an extremely elliptical orbit, whose pericenter is located just 2 kiloparsecs from the galactic center. This orbit also brought it near the Large Magellanic Cloud, or LMC, a one-armed spiral galaxy, and the Milky Way's largest and brightest satellite, about 75 million years ago.
Discovered in 2017 by the Dark Energy Survey, hence its name, DES J0225 plus 0304, or what we'll be calling 0304 from now on, is a faint object just 37 parsecs across, 240 times the luminosity of the Sun, and just 23.8 kiloparsecs from the Sun. It lies in an ambiguous state between galaxy and star cluster, but its luminosity suggests it is the former. Its proximity to the orbital plane of the Sagittarius dwarf spheroidal galaxy, which we will soon be seeing more of, suggests that both it and DES J0111-1341, its smaller non-galactic partner discovered at the same time, may be fragments of that galaxy that broke away as it was distended by our galaxy's tidal forces. This would make 0304 the nearest satellite galaxy of a satellite galaxy. Its metallicity of 5.5% that of the Sun, which is actually quite high for such a small object, suggests that it has not undergone much star formation over its lifetime, and it probably stopped billions of years ago. Actually, after its confirmation as a galaxy, 0304 was going to be named Cetus III, but a year after it was discovered, another galaxy was discovered in Cetus, stealing the name Cetus III from 0304.
The next stellar suburb out, at 25.3 kiloparsecs, is Cetus II. At about 34 parsecs across, and shining with the light of just 86 suns, Cetus II is far more solidly on the galaxy side of the ledger, though it still lies in that gray zone where definitions are unclear, a position planets know all too well. The stellar demography of Cetus II suggests that it comprises a single population of stars, all about 11.2 billion years old. Its metallicity, the main mark of age, is similar to the previous galaxy, at 5.2% that of the Sun. This metallicity bears the fingerprint of the Sagittarius dwarf spheroidal galaxy, in whose stream Cetus II, like 0304, resides. However, the galaxy does not appear to possess any form of stellar overdensity at its center, suggesting it may not be a galaxy at all, but rather a cluster of stars from the Sagittarius dwarf spheroidal galaxy's tidal stream that came together under their own gravity. Speaking of, the Sagittarius dwarf spheroidal galaxy. A solar cycle ago, when I was but a lowly Wikipedian, I struck up a correspondence with David Morrison, a research scientist at NASA, who had made the very 20th century mistake of attempting to engage with the public over the internet. After years of standing firm against the lahar of panic, rage, and recrimination this act of generosity inevitably triggered, he wisely decided to step back. Among the many cosmic tribulations the terrified public informed him were soon to be dealt humanity by an uncaring universe, and which Morrison, by dint of working at NASA, was implicated in concealing, was the Milky Way's impending collision with the Sagittarius dwarf spheroidal galaxy. Human ego being what it is, it would not occur to these hapless individuals that life has existed on Earth for 4 billion years, that our galaxy is 3 times older than that, and thus that any chances of any world-ending cosmic event occurring in their comparatively barely existent lifetimes are so infinitesimally low as to defy calculation. But then, these are the kinds of people who buy lottery tickets. It is an inescapable truth that our galaxy is in the process of consuming the Sagittarius dwarf spheroidal galaxy, as it has been for the previous 8 billion years. In fact, it is currently only about 6 kiloparsecs from the Milky Way's disk. But galaxies are such vaporous, ephemeral structures that expecting the collision to have any perceptible effect is like watching 2 trails of smoke converge and expecting the individual particles within them to collide. Less so, in fact, since the Sagittarius dwarf spheroidal galaxy is barely a 4,000th the Milky Way's mass. If the Milky Way were conscious, and who knows, it would register the impact as much as I, a slightly overmassed human being, would notice the added weight of 4 sheets of paper. The Sagittarius dwarf spheroidal galaxy, not to be confused with the Sagittarius dwarf irregular galaxy, because concision is not a word astronomers know, but to be confused with the Sagittarius dwarf elliptical galaxy, because they're the same thing, is, at about 400 million solar masses and about 300 million stars, the largest of the local group members we have encountered so far. It is also, depending on your viewpoint, either one of the largest objects in our intergalactic vicinity or the largest, and was discovered either in 1994 or 1778. Now, before you swear off science and join the doomsayers, let me reassure you that it gets much less confusing from here. The Sagittarius dwarf SAF is composed of 3 loosely connected pieces. The galaxy itself, sometimes called the remnant, lies beyond the galactic bulge, and so was only discovered indirectly in 1994. It is also why SAF lies 26 kiloparsecs from the Sun, but 6 kiloparsecs from the Milky Way. The Sagittarius stream is the gossamer trail of stars SAF has shed in its many journeys around our galaxy, looping over our galaxy's poles in a great elliptical river of stars. And finally, M54, a globular cluster discovered by astronomer Charles Messier in 1778, now believed to be SAF's defrocked core. SAF itself is an olive-shaped structure about 5,000 parsecs across, which, if it were visible to the naked eye, would be the largest object in our sky after the Milky Way itself. It is oriented top to bottom relative to the galactic plane, and is about 3 times as long as it is wide. This distension is caused by the immense tidal force of the Milky Way. Just as the moon creates a bulge in the ocean that produces the tide, so the Milky Way pulls its sap, stripping it of its stars as it spirals towards its doom, which it is expected to meet in about 1 billion years. It is estimated that about 10% of the stars in the Milky Way's halo are SAF refugees. This depletion also applies to gas, as SAF is exceptionally hydrogen poor and likely has not seen star formation in the last 5 billion years. The Sagittarius stream, which follows SAF's orbit, encloses a vast 100 kiloparsec diameter that, if you considered it a structure, would be the largest known in the local group, though no way the most massive. The entire stream, across its vertiginous, staggering expanse, is believed to comprise just 100,000 stars, or the typical population for a single large globular cluster. The stream itself is home to at least 2 globular clusters, with several more intriguing candidates, possibly relics from previous orbits. The stream is also divided in 2, a metal-rich bright stream and a metal-poor faint stream. Studies of metallicities in the stars within both streams show that they cut off after about 5 billion years, suggesting that is when the hapless galaxy's terminal journey began. The fainter stream, however, has no stars younger than 10 billion years, suggesting it was part of an outer halo that the Milky Way slurped off before tackling the tastier middle. The final course of this meal is M54, the globular cluster believed to have once been this galaxy's central bulge. SAF is home to at least 3 other globular clusters, with several other candidates, but these are relative tiddlers in the 10,000 solar mass range, while M54's mass is 1.5 million solar masses, about a third the mass of Omega Centauri, the largest known globular cluster. And, like Omega Centauri, there has been much speculation, though less in recent years, that it may possess a central black hole. Such a black hole would be a rare bird indeed, an intermediate mass black hole. Intermediate mass black holes are those above the 100 solar mass boundary for stellar mass black holes, but below the 100,000 solar mass boundary for supermassive black holes. Many have been hypothesized to exist, but as yet, none have been confirmed.
At about 27.5 kiloparsecs from the Sun lies yet another tiny galaxy, this time Hydrus I. It is slightly more impressive than most of the other specks of galaxies we have visited so far. At about 107 parsecs across, shining with a light of about 6,550 suns, and with a total stellar mass of about 6,000 solar masses, suggesting it may have around 20,000 stars in total. Quite a bit more than most of the others we have seen, but still a very far cry from the Milky Way's 150 billion stars or so. Hydrus I is exceptionally metal poor, with a metallicity of only 0.3% that of the Sun. Hydrus I is located about 24 kiloparsecs from the LMC, and has similar proper motion, suggesting it may be a satellite of the LMC. Analysis with data from the Gaia satellite's Data Release 2 confirms that Hydrus I is indeed a long-term satellite of the LMC, but it may not remain so for much longer, due to the Milky Way ripping apart the LMC satellite system.
Our next stop, Carina III, is also a bona fide satellite of the LMC, confirmed via Gaia DR2 data. Located about 27.8 kiloparsecs from the Sun, it's about 60 parsecs across and shines with the combined light of 780 suns. Carina III is also very elongated, being over twice as long as it is tall. Discovered in 2018, Carina III is also the first galaxy discovered which contains no RR Lyrae stars, an important standard candle.
At first glance, Triangulum II, also known as Levens II, named after astronomer Benjamin P. M. Levens, seems like a regular, albeit extremely small dwarf galaxy. Located about 28.4 kiloparsecs from the Sun, it's only about 32 parsecs across, and shines with a light of just 370 suns. Its total stellar mass is estimated at 897 solar masses, and so it may have about 3,000 stars in total. Star formation has largely ceased in Triangulum II since about 12.9 billion years ago. just 900 million years after the start of our universe. However, assuming that Triangulum II is in dynamic equilibrium, it is one of the densest and most dark matter-rich galaxies known, with a mass-luminosity ratio of 3600 solar masses for every solar luminosity. This also makes the galaxy an excellent place to observe the detection of possible gamma rays from the annihilation of dark matter particles.
Located just over 30 kiloparsecs from the Sun, Reticulum II is another ultra-faint dwarf galaxy, which has recently been captured by the LMC, within the last billion years. It measures approximately 97 parsecs across, and shines with a total brightness of 3,100 suns. Reticulum II's total stellar mass of 1,000 solar masses suggests a star count of about 3,300 stars. Reticulum II is also quite elongated, being about 2.5 times as long as it is tall. Most of the stars within Reticulum II exhibit an unusual abundance of so-called R-process elements, which are about half the heavy elements with nuclei larger than that of iron. They were likely created early in the galaxy's history by such extreme and energetic events as core collapse supernovae and neutron star mergers.
Next is the Coma Berenices dwarf galaxy, located about 33.4 kiloparsecs from the Sun. Coma Berenices is your typical faint dwarf spheroidal galaxy, nothing too special. It has a diameter of about 109 parsecs and a total visual luminosity of about 2,750 suns. Coma Berenices' average metallicity is also extremely low, at about 0.4% that of the Sun.
Next out, at 33.9 kiloparsecs, we find Carina II. About 171 parsecs across, and 4,750 times more luminous than the Sun, Carina shares a metallicity fingerprint with the satellite galaxies of the LMC, suggesting it is one as well. This is confirmed from analysis of its proper motion from data from Gaia DR2. It has a low metallicity of just 1.6% that of the Sun, and the majority of its stellar population is believed to be about 10 billion years old.
36.6 kiloparsecs out and about 80 parsecs across, we find Segue II. It's also very faint, just 520 times more luminous than the Sun, despite weighing in at a total mass, not just stellar mass, of 150,000 solar masses or less, meaning there are 360 or less solar masses for every solar luminosity in this galaxy. That mass also makes Segue II one of the least massive galaxies known, well below the supposed 10 million solar mass threshold needed for galaxies to form. This suggests that Segue II may be the darkened ruins of an ancient galaxy that was stripped of its material eons ago by the tidal forces of the Milky Way. The metallicity of its stars is very low, just 1% of the Sun, suggesting that star formation ceased in Segue II 12 billion years ago, not long after the formation of the universe.
Discovered in 2004 and named for Vera Rubin Observatory advocate Beth Wilman, Wilman I is slightly brighter than Segue II, with a luminosity of about 880 suns. Located 38 kiloparsecs out and about 56 parsecs across, its faintness suggests it may be dominated by dark matter, though determining its dark matter content is difficult due to its odd stellar motions, which indicate it may be in the process of disruption by the Milky Way. It's likely to be quite dark matter rich, with an estimated mass-to-light ratio of 800 solar masses per solar luminosity. The stars in Wilman I are all ancient, with metallicities less than 1% that of the Sun, and thus likely more than 10 billion years old.
Boötis II, or more adorably Boo II, is another faint, small and old galaxy, located just under 42 kiloparsecs from the Sun. It's about 1,300 times brighter than the Sun, about 78 parsecs across, and has a metallicity of just 0.2% that of the Sun. This suggests its stellar population is old, mostly between 10 to 12 billion years old. Although close to the galaxy Boötis I, it shares no motion with it, and is more likely associated with the Sagittarius stream.
46 kiloparsecs out, we arrive at Ursa Major II. At 365 parsecs across, and shining with a combined brightness of 8,700 suns, UMA II is fairly hefty compared to what we've seen so far, but with a mass-to-light ratio of 4,000, it's believed to be one of the most dark matter-dominated galaxies in our local universe. Of the stars it does have, their metallicity is just 0.3% that of the Sun, low even by this sample's standards, indicating that it is a dark relic from the ancient era of the universe, at least 10 billion years ago. Its total stellar mass may sit near 8,500 solar masses, suggesting it may have a combined stellar population of around 28,000. Much like Saf, it is distorted into a cigar shape by the tidal forces of the nearby Milky Way. Among the many streams circling our galaxy, there is one known as the Orphan Stream, because no one can determine exactly who is laying it. Because UMA II's motion appears to follow the Orphan Stream, some have speculated in the past that it may be the stream's origin.
45.7 kiloparsecs out, we arrive at Pictor II. Discovered in 2016, it's about 96 parsecs across, its luminosity is just over 1600 suns, and its stellar mass is also about 1600 times that of the Sun, suggesting a total stellar population of just over 5,000 stars. Its average metallicity is 1.5% that of the Sun, which actually is relatively high for such a small galaxy. Its position and motion suggest it may be a satellite of the Large Magellanic Cloud. Simulations of the interactions in the Milky Way system between our nearby dwarf galaxies and the Large Magellanic Cloud suggest that this is the case.
48 kiloparsecs out, we arrive at Tucana IV. No, not Tucana IV, the rape-happy homeworld of Star Trek character Tasha Yar, but another faint metal-poor galaxy. Its metallicity, at 0.3% that of the Sun, is similar to Ursa Major II and other tiny galaxies. At a total mass, not just stellar mass, but also dark matter, of 2.2 million solar masses, and 254 parsecs across, it is one of the larger objects in our sample. Despite this, its luminosity is just 2,150 times that of the Sun, quite low for such a relatively large galaxy, giving it a mass-to-luminosity ratio of about 2,000, suggesting it has quite a lot of dark matter. Well, that was a fairly homogeneous string of galaxies to end on. That said, the next galaxy on our list, the Large Magellanic Cloud, is going to need quite the introduction, and so it seems prudent to stop here. If you enjoyed this journey, please remember to like, comment, subscribe, etc. And thank you again to Trolligi for making it possible. And I will see you again, fellow seekers, as we enter the arms of Andromeda.